If you didn't have CAD to draw pictures of arrows, but you had some kind of a calculator, you could use a thing called X and Y components to figure out any of your forces. And in fact, that's what engineering students have to do. Many students don't learn the graphical method that you're learning, and so they have to use X and Y components. So let's see what those are. Remember how we saw this bolt with these two forces, 500 and 1200, and we could take those two forces and make a parallelogram. And that diagonal turned out to be the resultant. So taking those two forces and replacing them with a single force gave us the same net result. You could also work back the other direction. You could start with the resultant and resolve it into the two components, and they have the same net result. So here's a slopey force, here's two horizontal and vertical forces. They have the same net result as that slopey force. The two components of a force have exactly the same result and same effect as that one slopey force. So for example, kicking a soccer ball at a 50-degree angle would have the same net result as two unfortunate people hitting the soccer ball horizontally and vertical at that point. Or here's our motorboat. The X component, the horizontal current, and the Y component, the vertical motorboat force, have exactly the same result as that slopey resultant force. In fact, there are an infinite number of combinations you could do. Here are three drawings with the same resultant arrow, same length, magnitude, same angle and sense, with several different examples of combinations of two forces, two components, that you could add together and make that one resultant. But the most useful kind of pairs are rectangular pairs where you have one component is horizontal and one component is vertical, because those are easy to do even if you don't have CAD. So if you were looking at this force pulling at a 30-degree angle, it might be easier to think about the X and Y components of that force, and you would find them by drawing a parallelogram around that force. There you are. And the horizontal side of that parallelogram is called the X component. The vertical side of that parallelogram is called the Y component. Many people like to use trigonometry to find those X and Y sides of those parallelograms. And as we saw in the previous video, when you're figuring out, let's say the sine equals opposite over hypotenuse, you can rearrange the terms and put hypotenuse times sine equals opposite. So people do that quite a bit. Or for cosine, hypotenuse times cosine equals adjacent. Okay, now we have two problems that we're going to work on. And the first one here, we have a 1,000-pound force pointing at the end of this steel beam. And unfortunately, they don't tell us the angle of that force. They do tell us that it's sitting at a 3 to 4 rise over run ratio. Now remember our friend the Pythagorean triple? A couple times ago we saw a 3, 4, 5 triangle. All right, so one thing you could do is think about, okay, this must be a 3, 4, 5 sort of ratio, or a 30, 40, 50 ratio, or a 300, 400, 500 ratio, and so on and so forth. and from there work backwards to figure out, okay, if this is 1,000, then how big are these two? That's one thing you could do. Another thing you could do is you could use trig to figure out how big one of the angles was, as long as you made sure you don't round off. And a third thing you could do is draw this in CAD. Now, it's a really good idea to do a problem more than one way. If you get the same answer both ways, you can feel pretty certain that your answer is right. If you get two different answers, then something went wrong somewhere and you need to go back and check. So if I were doing this problem, I think I would try the ratio thing because I'm not very good at that, and that's something I want to get better at. So I would try the ratio thing and see if I could figure out how big the x and y components were. And then, to be honest, I would go back and draw that thing in CAD and and make the hypotenuse 1,000 things long and measure the two other sides and see if I came up with the same number. And hopefully I would. Hopefully you will. So that's the first problem. Here's the second problem, written in the way that these engineering books like to write. So we've got a hook or a screw eye screwed into the ceiling, and he says the hook can sustain a maximum withdrawal force of 250 newtons in the vertical direction. All right, so first of all, this problem is in metric units, not imperial units. So newtons is the force instead of pounds, but that's okay. Then he says it can sustain a maximum withdrawal force. What he's trying to say is, if you pulled straight down with 250 newtons, if you pulled down with just a hair over 250 newtons, that thing would pull out of the ceiling. So up to 250 newtons pulling straight down, it will hold. Beyond that, it won't hold. Now in this screw eye, we have a rope where we're for some reason having to pull at a 10-degree angle away from vertical. The question is, how hard could we pull on that rope before we pulled the screw eye out of the ceiling? So in other words, you have a triangle here, and you know the angle is 10 degrees, and he has in effect told you the y component. He's told you the vertical leg of the triangle, and you're trying to find the hypotenuse of the triangle. So you might try actually just sketching a triangle. I think that's what I would do. I'd make the vertical leg 250. I'd make the angle 10. I'd write an H over here, and then I'd try and calculate that. And if you want to check yourself, try drawing that triangle in CAD and see if you come up with the same answer you did when you did trig. Another way to check yourself, by the way, is just to look at this situation, this triangle situation, and think about what would you expect? Which side of the triangle would you expect to be longer or bigger? And just by sketching that triangle, you would realize, oh, the hypotenuse, that tension on the rope, the hypotenuse is going to have to be a little bit longer than that vertical leg of the triangle. So when you do your trig, or you check it in CAD, you should come out with a hypotenuse that's just a little bit bigger than 250. Not a lot, but a little bit. And if it's way off, or if it's smaller than 250, then you know, oops, went the wrong direction, try it again. So that's another way to check yourself. Okay, well go have a run at those two problems.